Hello everyone. So today's class is going to be about nucleophilicity. So the term looks a bit complex, but it is actually not, and it's actually going to be very interesting, right? So we use this term nucleophilicity in case of nucleophilic substitution reactions, and as the name tells you, nucleophilic substitution, where one nucleophile replaces another nucleophile from its compound. Now the first question comes to our mind is, what is a nucleophile, right? And the answer lies in that term itself. Nucleo is nucleus, which means a highly positive charge, and phile means loving. So anything which has high affinity for positive centers are what are called as nucleophiles. So the term nucleophiles means basically positive loving. Right. Now the next question comes is, what kind of species can be positive living, or what kind of species can be nucleophiles? Now it's very simple. So for me to have attraction towards positive charge, definitely it should be a negative charge. Now in chemistry we deal negative charges in terms of electrons, obviously. Now the question is, this nucleophiles, based on how they have this excess negative charge, that is how they have this excess negative charge, is going to depend upon two things, right? One, it can either be a charged nucleophile or it can be a neutral nucleophile, right? So if that's the case, again we have to see what exactly are these two, right? So again, as the name tells you, charged nucleophiles are going to be negatively charged, so that they are going to be positive loving species. Say I can give you a humpty number of examples: OH minus, Cl minus, H minus, R minus. So you can see all of these has negative charges associated with them, right? Now when I go to neutral nucleophiles, yes, I am going to have affinity for the positive charges, but as the name tells you, I am not going to have any excess negative charge. I am going to have higher number of electrons in terms of lone pairs, and these lone pairs have the affinity for the positive centers. So again I can give you a humpty number of examples. Say NH3, where nitrogen is having a lone pair, H2O, where oxygen is having the lone pair. So you can see thus the nucleophilic centers in these cases are going to be the lone pairs on nitrogen and lone pair on oxygen, right? So now that we understood what exactly are nucleophiles, now what I am trying to tell you is, okay, we will move on. So now that we have a grasp of what exactly nucleophiles are, first let me give you a general equation for a nucleophilic substitution reaction, right? So the reaction goes like this. I have some RLG. LG represents leaving group, which is going to come out from this substrate, and I am going to have the incoming nucleophile. I am going to represent the nucleophile like this with a negative charge. Now the overall reaction goes like this. Now it is going to be a simple displacement reaction which you have already learned in chemistry. In your lower classes you would have learned a highly reactive species displaces the less reactive species from its compound, and the same thing happens here. So I am going to have a bond formed between the alkyl group and the incoming nucleophile, and I am going to have the leaving group to be coming out. Now this is a simple nucleophilic substitution reaction, right? Now let me give it some interesting facts. Say for example, I have RCl and I put NaOH. So you can understand that the incoming nucleophile is going to be OH minus, and Cl minus is going to get replaced with this. So I am going to have ROH plus NaCl, right? Now I will do one more thing. I say I have ROH and I put NaCl. Now what you see is I have Cl minus as the incoming nucleophile, and I'm going to, and if you expect that this reaction is going to happen, no, this reaction will not happen. But this reaction happens, but this reaction doesn't happen. Now this is where this term comes into the picture, right? So nucleophilicity in generic terms just talks about the reactivity of the different nucleophiles. If I have a highly reactive nucleophile, that highly reactive nucleophile will be able to displace a less reactive nucleophile, or in terms of speaking in terms of nucleophilicity, A nucleophile having high nucleophilicity will be able to replace the nucleophile with less nucleophilicity, right? So I think now you got the broader picture. We'll move on. So what we have to understand is how are we going to determine this nucleophilicity. So nucleophilicity basically talks about the affinity, how much love it has for the positive center, right? Okay, now how are we going to decide this? How, like, depending on obviously so many factors I'm going to give you now. Based on all these factors, using all these factors, I'll be able to determine, okay, this nucleophile has better nucleophilicity and this nucleophile is a poor nucleophile, or it is having very less nucleophilicity. Now what we need to understand is this nucleophilicity is going to be a kinetic term. So again, whenever kinetics come into the picture, we speak about how fast this reaction happens. Say if I have a positive center, say R plus, and say I have a nucleophile, right, and I'm going to form R and U, right, how fast this chemical reaction happens depends only on the nucleophilicity of this nucleophile, and that term is what is nucleophilicity. Okay, now moving on, now we'll see what are all the factors which are going to affect this nucleophilicity. Okay, now first and foremost thing, basicity or basic strength is always proportional to the nucleophilicity. So what I'm trying to tell you is that generally strong bases are good nucleophiles. They have high nucleophilicities. Okay, now however, let me take some examples and then we'll work it out. Say for example, I have CH3 minus and say I have OH minus and say I have Cl minus. Okay, so I have to determine the order of their nucleophilicities, right? Okay, now I think in the chapter of equilibrium, you would have understood how do we determine the strengths of acids and bases, right? So now what I'm trying to do is that, or before that, what you have to understand is the concept of conjugate bases and acids, right? Now always remember, if I have an acid which is very strong, the conjugate base of that strong acid is always weak. So strong acid, weak conjugate base, weak acid, strong conjugate base. So it's always ulta pulta, vice versa. So now let me write, so hope you understand what are conjugate acids and bases. For example, let me just give you a small example. I have HCl to be an acid. So what is the conjugate base of HCl? Remember, for any conjugate base of an acid, just remove the H plus and whatever is remaining after that, after the removal of H plus, is what is my conjugate base. Now after removing H plus, minus H plus, what is remaining here? Cl minus. So I am going to call Cl minus as the conjugate base of the acid HCl. Hope you understood. Now these are all the conjugate bases, right? So something I have removed H plus and these are all the remaining conjugate bases I have. Now so let me write what will be the acids, what can be the acids of all these conjugate bases. Now I can directly do the opposite of that, just I add H plus to all these species. So I can directly tell you that it's going to be CH4, it is going to be H2O, and in this case it is going to be HCl, right? So now as one point I told you, whenever I have strong acids, their conjugate bases are weak and vice versa. Okay, now try to understand, I already know HCl is a very strong acid, right? So if I just compare the acidic strengths here, the first rank goes to HCl, that is, it is the strongest of all acids. Now next, comparing CH4 and H2O, I know CH4 is amphoteric, that means it can be H plus acceptor as well as a H plus donor. But CH4, no, it's a neutral compound, it can neither give H plus nor give nor accept H plus. So the second rank goes to this and the third rank goes to this. Very simple, right? So you saw that this is the acidic strength order. So when I go for the conjugate bases, the opposite is going to be the order of their basic strength. So I can directly tell you CH3 minus is a better base than OH minus and OH minus is a better base than Cl minus. And obviously, going to the first point, basic strength being directly proportional to the nucleophilicity, this will be the order of nucleophilicities also. Okay, now this need not be always the point. There can be exceptions to this. Let me take an example. Okay, so let me take RS minus and RO minus. Cool. Right. So now if I check out of these two which is a stronger base, definitely RO minus is a stronger base, right? But again, RO minus is a stronger base, so I expect RO minus to be a better nucleophile or RO minus to have better nucleophilicity than RS minus, right? But the opposite is going to be true. The nucleophilicity order is going to be like this. So what I'm trying to tell you is that RS minus is going to be a better nucleophile than RO minus. Now we have to come up with a plausible explanation of why this happens like this. It's very simple. Now you have to understand from where the electron is going to attack the positive center, or by in more specific way, from which element the electron is going to go attack the positive center. Now you can understand that here oxygen is that element from where the electron goes, and in this case sulfur is the element from which the electron goes, isn't it? Now obviously one beautiful thing comes into the picture, and that is my electronegativity, right? So we know what electronegativity is, isn't it? Electronegativity is the ability of the element to accept the electron, how much love it has for electron. So if an element is highly electronegative, for it to lose electron, it is going to become more and more difficult. Now obviously I know oxygen is more electronegative than sulfur. So obviously removing electron from oxygen is difficult when compared to removing electron from sulfur, right? So definitely electrons from sulfur can easily go attack the positive center because of less electronegativity of sulfur, and in case of oxygen, because of high electronegativity, the electron from it will not be able to go that easily attack the positive center. So there can be exceptions like this. This is not like for basic general case, good bases, strong bases are good nucleophiles, but there can be exceptions also like this. Okay, now this is the first point. This is not the only factor. Moving on. Okay, now second is about the charged or neutral. Now for this, let me take a very easy example. Say I have H2O and OH minus, or say I have alcohol and say RO minus. Cool. Okay. Now let me see this. If I have an alkyl chloride RCl, if I either put H2O or if I put NaOH, or say directly putting OH minus, I am going to have I am going to have alcohol as the product in both these cases, right? Now as I already told you, nucleophilicity is a kinetic term. So if I look at out of these two, which reaction is faster, right? I found out that this reaction is faster, right? So now this is what we conclude. What we conclude is that whenever I have the nucleophilic centers to be same element also, right? But if at all in one case the nucleophile is charged and the other case the nucleophile is neutral, definitely the thing with a negative charge is having more nucleophilicity. So in simple words, OH minus is always a better nucleophile than H2O, and RO minus is always a better nucleophile than ROH. This is one thing. Okay, moving on. Okay, now third factor is going to be electron withdrawing groups or electron donating groups. Now this is going to be very logical, right? Now let me take an example. Say I have OH minus, I have CH3O minus, and say I have CH3COO minus. Or let me write it properly. Okay, this is a better way. Right, now I have to, again, this thing is that I have to arrange them in the order of nucleophilicities. Okay, now we'll compare these two, right? Okay, now along with oxygen I have an alkyl group, right? And here along with oxygen I have a hydrogen, right? Now look at this. Now remember CH3, all alkyl groups are electron donating in nature, right? Okay, now if that's the case, now we are talking about nucleophilicity, the ability of this element to donate the electron to the next species, the positive center. Obviously, if the attached group is highly electron donating, the availability of lone pair or availability of the negative charge on oxygen is actually increased. Is it not? Since it is electron donating, it is going to donate electron to the oxygen, making the availability of electron on this oxygen to be getting increased, right? So definitely keeping that in mind, hydrogen is not like that. Hydrogen is not electron donating in nature. So if I compare these two, definitely this is going to be a better nucleophile than this, because CH3 is an electron donating group, increasing the availability of lone pair on oxygen. Okay, going back to this, right? Now what kind of group? This is carbonyl group, CH3CO acetyl group. Now what you understand is the lone pair which is present here is actually involving in resonance, isn't it? So what I understood here, the availability of lone pair on this oxygen is actually getting decreased because of the effect of resonance happening here. So obviously when I compare this and this again is going to be a better nucleophile than this, because this is going to be an electron withdrawing group in terms of resonance. And here CH3 is an electron donating group, increasing the availability of lone pair on oxygen, right? Okay, now this is one more factor. Moving on. Fourth factor is going to be the steric hindrance. Now this is a technical word for the basic term of crowdedness, how fat or how big that particular nucleophile is. I'll go for an example. Say I have CH3O minus, this, and this. All are alkoxide ions, all of them have oxygen as the nucleophilic center, but all are electron donating groups, no problem. But the only thing which is going to vary is about the length of the alkyl chain, how big the alkyl chain is. Now again, making you remember that nucleophilicity is a kinetic term, it's about how fast the reaction occurs. It's all about a running race. We can take a general real life example. I have a guy who is little bit stout, and I have a guy who is very lean. So definitely a guy who is leaner can run faster. The same thing goes here. The thing which is having the least of all crowdedness will be able to move faster and go and attack the nucleophile in a more faster way. So keeping that in mind, I'll be able to easily arrange them in the order of nucleophilicity. This is the least crowded of all, so definitely this is going to have maximum nucleophilicity. Compared to this is secondary, this is tertiary, so definitely this is going to have better nucleophilicity than that. Simple. Now the last and the final factor, is presence of a protic solvent. Okay, so first, a protic solvent is one which can give me H plus, not exactly, or I would say whichever is capable of undergoing hydrogen bonding, or what are called as protic solvents. And the beautiful example of a protic solvent is water, right? Okay, now in presence of water there is going to be something strange happening, right? So let me now take an example. I have I minus, Br minus, Cl minus, and F minus. All are halogens down the group, up the group. Okay, so now let me use the first ever factor. The first ever factor was basic strength. right? So if I go along with basic strength, if I write the acids of all these, I have HI, HBr, HCl and HF. Again, if I can determine the order of acidic strength, the opposite is going to be the order of the basic strength, and so is the nucleophilicity. Cool. Okay. So out of all this, definitely I know HI is the strongest acid. Now again, the reason is because I will be able to break the IH bond very easily compared to HF bond. HF bond is very, very strong. So breaking it and removing H plus is very difficult, whereas in case of HI, it's very easy because the bond is very, very weak. So H plus can come out easily. So the order of acidic strength is going to be like this, no doubts. And obviously opposite is going to be the order of basic strength. So I can say that this will be the order of basic strength, the meaning that F minus will be a better nucleophile than Cl minus, than Br minus, than I minus. Okay. Now this is true if the reaction medium is not happening in case of water. That means the reaction medium is not water, right? But if the reaction medium is going to be an aqueous solution, or say the reaction medium is going to be in case of water, there is going to be some complications, and the complications are going to arise because of this phenomena, hydrogen bonding. Okay. Now we actually know what hydrogen bonding is, isn't it? So hydrogen bonding, or I would say hydration or solvation, is a phenomenon where I have an ion and that ion gets surrounded by water molecules, isn't it? So let me give you a small how it happens. Say in general I have a negative charge, right? So I have a water molecule, right? And I know OH bond is highly polar. That means I am going to have a partial negative charge on oxygen and partial positive charge on hydrogen, right? And there can be some kind of interaction. So between this hydrogen and this, again I can have one more hydrogen molecule which is having a positive charge, again I can have some kind of interaction. So many water molecules will be able to surround this anion. Okay. Now please understand, if this happens, right, can I indirectly say that the steric hindrance of the nucleophile increases? Is it not becoming crowded? Is it not becoming heavy? So therefore, whenever hydrogen bonding happens, whenever I have a protic solvent, hydrogen bonding will happen for the nucleophile, and because of that, the nucleophilicity of the nucleophile will get decreased because it is getting crowded. It will not be able to move as easily as the previous case, isn't it? So keeping that in mind, we'll take the same set of 4 examples, that is I have I minus, Br minus, Cl minus and F minus. Okay. Now in all of them hydrogen bonding is going to happen. So in general, if I have a protic solvent, the nucleophilicities of all these anions are going to get decreased, no doubt about it, right? But the next question is, to what extent in each case, right? Now please understand that the hydrogen bonding is going, or the amount of hydration is going to depend upon the size of the nucleophile, or I would say size of the anion. Now it's very simple. If I have a very small anion, right, the probability of it getting crowded is very, very high, right? But if I have a very big anion like this, the probability of this getting crowded is going to be very much dispersed. I am not going to have a very concrete crowding. But in this case of a very small anion, the crowding can be more and more efficient. And obviously, more and more efficient hydrogen bonding, less and less will be the nucleophilicity. Now, I think I made it clear. Again, I repeat, you have to understand that the smaller anion can get crowded very easily, or in other words, it can be solvated or hydrated easily because of its very small size. In case of a big anion, the crowding is going to be very, very difficult. So the extent of hydrogen bonding will be lesser and lesser as the anion size becomes bigger and bigger. Keeping that in mind, we obviously know that the smallest of all the anion is F minus, and the biggest of all the anions here is I minus. So now the first question is, where I can have the hydrogen bonding to be maximum? Definitely in case of F minus. And where I can have the hydrogen bonding to be minimum? Definitely in case of I minus. And as I already told you, if the extent of hydrogen bonding is higher, the nucleophilicity is lesser. So keeping all that in mind, I think we'll be able to easily bring out the picture here. What will be the order of nucleophilicity if I have a protic solvent in the picture, definitely I minus is going to be least crowded, so its nucleophilicity is maximum, and then Br minus, then F minus. Now if you look at this, and if you just look at previously how we did the order of nucleophilicity without the protic solvent, we actually got the opposite order. Right, that's why I told you basic strength is not the only criteria. There are other criteria, say for example the electronegativity of the atom, and say if you have a protic solvent, all those matters. So in the next class we'll be able to see something about the leaving groups and about what exactly is the mechanism of a nucleophilic substitution reaction. So I think it all went good. Thank you so much.